Electron Configurations. 3 rules for filling electron orbitals. 1. Aufbau Principle. Electrons are added one at a time to the lowest energy orbitals available until all the electrons have been allocated. 2. Pauli Exclusion Principle. An orbital can hold a maximum of 2 electrons. To occupy the same orbital, 2 electrons must have opposite spins. End quotes there, because they're not really spinning. Hund's rule: if 2 or more orbitals of equal energy are available, electrons will occupy them singly before filling orbitals in pairs. Aufbau takes its name from a German word meaning building up. It was developed in the 1920s by Bohr and Pauli and states that electrons fill the lowest energy levels, down here, first. 1s fills up first, then 2s, then 2p, then 3s, then 3p. But wait, the 4s level has less energy than the 3d level. What happened? Well, that's because the orbital energies depend on the n quantum number and the L quantum number. And now that's beyond the scope of this course, but we just have to know how they fill up here. Pauli Exclusion Principle. No 2 electrons in the same atom can have the exact same quantum numbers. So this is correct. Okay, right? 1s2 has 2 electrons, 1 up, 1 down, and that's the spin. 2s2, 1 up, 1 down, 2p, 1 up. That's great. This is not right. You can't have 2 spin ups in one orbital because they have the same quantum numbers there, so that's no good. And Hund's rule. Every orbital in a subshell is singly occupied with 1 electron before any one orbital is doubly occupied. And all electrons in the singly occupied orbitals have the same spin. So here we have 1s2, 2s2, that's good. Then we go over to 2p, okay? We have 2 electrons. We have 3 different orbitals. So we have 1 in the up direction in the first one, and then 1 in the up direction in the second one. That's good. We can't double up yet because we haven't filled everybody. So this is incorrect, right? Because we've got a double here in 2p2, and we didn't have anybody here yet, so that's no good. Electron configurations show the distribution of all the electrons in an atom. Each component consists of a number denoting the shell, right over here. That's the N number. Then we have a letter denoting the type of subshell. In this case, it's P, right? We had S, P, D, F. And finally, we have a superscript denoting the number of electrons in those orbitals. So you would read this as 4p5. So much going on in this chart, so you may want to pause this after I talk about it for a while. So we're going to go with the elements from hydrogen in order of increasing atomic number. And the first thing we fill is the 1s1 electron. And so this is the diagram, the Aufbau diagram, and here's how you write the configuration, 1s1. Then helium adds another electron, and that has to be opposite spin. So you went spin up, then spin down, and we call that the 1s2. Lithium, we add an electron here in 2s, so it's 2s1. Carbon, now we have another electron here. Spin up, spin down, and then it looks like we're over in the p shell now, and we've added 2 electrons there, and notice we fill up each separate p orbital by itself before we double anybody up. So that's 1s2, 2s2, 2p2. Let's just do a couple more. Nitrogen, you add another electron, and you don't double up any of them. You fill that 3rd p orbital. And again, note they're all in the up direction, spin up. And then we'll stop with oxygen. Now we add our 4th electron to the p shell, and we put that in the first one with a spin down, and we represent that as 1s2, 2s2, 2p4. And here's the ground state configuration of sodium, 1s2, 2s2, 2p6, 3s1. All of the superscript numbers add up to the total number of electrons. So please remember, in a neutral atom, the number of electrons equals the number of protons, which is 11 down here, the atomic number. So let's see, 2 plus 2 is 4, 10, 11. Yep, checks out. Electron configuration of Krypton, element with, let's see, 36 protons and 36 electrons. Now the configurations are based on the energy level of the subshell, not the shell. Remember we said earlier that the energy depends on both the shell and the subshell, the N quantum number and the L quantum number. So here's Krypton. 1s2, 2s2, that's pretty good. 2p6, 3s2, 3p6, so far so good. But then we have the little thing here, the 4s2 has a lower energy than 3d10. So here it is. Here's your 4s2, and then here's 3d10. And then on top of that would be 4p6. Example 1, magnesium. Fill in this diagram for magnesium and write its electron configuration. So the first thing you have to do is consult your periodic table, find out the atomic number, and that will be both the number of protons and the number of electrons. And then use the 3 rules, the Aufbau, Hund, and the Pauli exclusion principle. Well, the atomic number from the periodic table is 12, so we need to fill in 12 electrons. So let's keep a running tab here. Do 1s2, we go from lower energy to higher energy. So 1s2, that's 2 electrons. 2s2, another 2 electrons. And then 2p6 and 2, 4, 6. So 1, 2, 3, 4, 5, 6. Then we have 2 more electrons and they go into the 3s shell. So 1s2, 2s2, 2p6, and 3p2. Now let's do chlorine. So again, go to the periodic table, find its atomic number, and start filling up the orbitals using our 3 rules. Now let's do chlorine. We find that Z is equal to 17, so we need to place 17 electrons. So let's just check if we have it right here. 2 plus 2 is 4, plus 6 is 10, plus 7, 17. Okay, that's good. So we start at the bottom, 1s2, that takes 2 electrons. 2s2, 2 more electrons. 2p6, that places 6 of them. 1, 2, 3, 4, 5, 6. 3s2. And then 3p5. 1, 2, 3, 4, 5. Yep, 17. That's good. Now let's do iron's electron configuration. Iron electron configuration, we look it up on the periodic table or just Google it, and you get Z is equal to 26. So let's check if we've done this right. Let's see, 2 plus 2 is 4, 10, 12, 18, 20, 26. Excellent. So we start as before, we fill in the lower energy orbitals, and we're good up till 3p, and then instead of going to 3d, we have to do 4s. So we fill that with 2 electrons, and in 3d, first you fill each orbital separately with the spin up electron, then you have 1 left over. That goes into the first box. And you write that as 1s2, 2s2, 2p6, 3s2, 3p6, and then the 4s2, which dropped in energy below the 3d6.